Hi guys, BuildZoid here, and today we're going to be taking a look at the Maximus 11 Gene from ASUS. So I actually managed to buy one of these here in the UK. Apparently the board is kind of Europe exclusive right now, and it's actually restricted to only a couple retailers. Because I know, say, Alza wanted to carry this board and they can't. But OC UK, and I think so, and if OC UK has it, then Case King also has it. But right now this board is basically kind of in a weird situation availability-wise, which I don't get, because I'm sure there's lots of people in the US who would want it. So yeah, I'm not sure why they're restricting it only to Europe. It doesn't really make any sense to me. And the other thing is, this board is extremely expensive. So huge thanks to the fan of the channel who basically paid for it. Not basically paid for it. He literally paid for the board. He was like, "Hey, BuildZoid, I want you to review a Maximus 11 Gene. Here's the money to buy one." And so here we have the Maximus 11 Gene. It was 300, like in the UK right now at OC UK, it's 310 quid for the board, and that's including taxes, of course. So if it does end up in the US, it'll probably end up somewhere around $300 to maybe $320. So yeah, it's by no means a cheap motherboard. Anyway, with that out of the way, let's get right into sort of the features, and then eventually, of course, the VRM here. So right off the bat, we have dual 8-pin power connectors. Like most sort of high-end Z390 motherboards, you do not need to plug in both of these unless you're on some kind of exotic cooling setup, which means like delidded with a lapped die, potentially sub-ambient cooling, so like water chiller or phase change, you know, LN2, that kind of thing. So basically, if you're on just normal cooling, you don't need to worry about the second 8-pin. You don't need to plug it in. If you are on sub-ambient, it may help to plug the extra 8-pin power connector in. Of course, plugging in the extra connector also does no harm. So if you have the connector available and it doesn't screw up your cable management or whatever, then, you know, there's no reason not to plug it in either. But it's not required for the motherboard to run. You can just plug in the first one. In fact, I'm not sure the motherboard will care if you plug in either of them, because like at least my Maximus now, like, because these are almost certainly just straight up parallel with each other, as in like all the 12-volt pins are on the same power plane and all the ground pins are on the same power plane. So, you know, it won't really, like, the board doesn't even know which of the connectors would necessarily be plugged in. So yeah, that's that. And moving on to the other sort of features of this board, we have the Memo K switch, which it's supposed to disable and enable the motherboard's retraining capabilities, which to me just sounds like a really, like I'm not sure that's going to be all that useful. Generally speaking, if a motherboard can't train memory, then I just, like, I'm not seeing it. Like, usually that's a situation where I would resort to the safe boot button or the retry button. I'm not sure that this switch is going to be all that helpful, but we'll see. I've not yet tried the motherboard out, but, you know, this might actually be helpful, and I'm wrong, but on paper, having the motherboard automatically retrain the memory over and over and over again generally just leaves you stuck in a boot loop, and most motherboards do that even without the switch. So I'm really not sure why that is like a new feature that they added. And of course, much more useful, we have the postcode, great for troubleshooting all kinds of issues. You know, you just look up whatever error you get in your motherboard manual, and then you can go from there. Below that, we have some troubleshooting LEDs, which are color-coded, so you can see what kind of problem you have at a glance, instead of like having to memorize postcodes or something. Well, like, get a rough idea of what problem you have at a glance, because obviously this is going to be like, oh, you have some generic boot device error, or you have some GPU error, whereas this will be like, oh yeah, failed at, you know, memory training, and failed at chipset initialization. You know, this is much more detailed, but this will give you a pretty good idea of what exactly, like, what part of the system isn't working. Below that, we have the LN2 mode jumper. I'm not a fan of jumpers, but I assume ASUS is putting LN2 mode on a jumper because they don't want people who shouldn't be using LN2 mode enabling LN2 mode by accident. And putting it on a jumper makes it probably just seem a little bit more special to the average user. The LN2 mode on most ROG motherboards, it sets up some of your voltages for you, but it also, what the main thing it does is it lifts all of the safeties. So your V-core can go to levels that will very quickly turn your CPU from working to a keychain, or, you know, a desk ornament, if you're into that sort of thing. And the same goes for like memory voltages and really all of your voltages. Like it just takes off all of the voltage restrictions, power restrictions, all of that stuff. So yeah, and it's really meant for extreme overclocking, which is why it's called LN2 mode. And that's a nice feature. Well, I'm not sure how I feel about this. I guess it's a nice idiot proofing thing on ASUS ROG boards. Ultimately, I don't care that much because I end up running the boards in LN2 mode all the time in anyway. Below that, we have the slow mode switch. Now, this is super handy as far as I'm concerned because this allows you to force the CPU into the lowest CPU ratio possible. So I think with a 9900K, that's going to be 8x. And so instead of idling in like, let's say you're on LN2, you get into Windows, right, and you're just setting up some software things. Well, there's no reason to be doing that at 6 gigahertz. You could be doing that at like a gigahertz instead. So you can flick the slow mode switch and put the CPU at 8x CPU ratio, and basically it massively reduces your power consumption. It also reduces the probability that you're going to crash because you're going to be running so much slower. So pretty handy for just like for extreme overclockers. It's not really, I can't really see a reason why it would be that useful for anything else. Below that we have the reserved switch, so the RSVD. And the RSVD switch, what that does on ROG boards, it will it'll set up a bunch of voltages for you that will remove the cold bug and cold boot bug on Coffee Lake, and they've had it on the previous, like they had it on Z270 and I think X299 and like a bunch of other platforms. But here, of course, it'll remove the cold boot bug for your cold bug for your 9900K. There's basically sort of 5 voltages that you need to set to very specific levels in order to get these CPUs to work below minus 120 degrees Celsius. So that switch takes care of that for you, and basically you have to, like, it reduces the amount of effort you need to go to get the system running. Obviously you can learn all, like, what to set those voltages yourself. To yourself. Also, this switch only works with something like 90 or 95% of CPUs. Some CPUs will not work with the voltages that this switch loads up, and it also changes like 7350Ks would use completely different voltages from 7700Ks. 9900, well, some 7350Ks. I have a 7350K that is like the antithesis of my 7700K. My 7700K on the Z270 Maximus 9 Apex works great with the RSVD. The 7350K absolutely hates that switch. Like, that switch doesn't do a damn thing for that CPU. So that one has to be manually tuned. I think there's a similar issue between like 9900Ks and 8700Ks. So like going from 6-core Coffee Lake to 8-core Coffee Lake, there's actually some similar voltage differences. So yeah, this switch, like, very, very handy most of the time. Not always. It's not always going to work with all CPUs perfectly, but definitely if you have a CPU that does work with it well, you know, this makes your life so much easier. Below that, you have the power switch. Oh, and this is literally only for liquid nitrogen overclocking. In fact, if you enable this at like 0 degrees Celsius or at like ambient temperatures, the system will not post. And that's not because there's some kind of safety tripping. It's just the voltages it sets up will literally cause instability if the system is too warm. So this is like, you should enable this switch at like minus 100 degrees. At higher temperatures, it doesn't even work. So that's worth noting. Power button, reset button, retry button. So this button is like a forced reset. Basically, if the system becomes unresponsive, you know, locks up, reset button doesn't work, power button doesn't work. I mean, you can hold this for 10 seconds, but holding this for 10 seconds is a lot longer than just mashing the retry. The retry will always get the system to reset. This is also great if you have certain, like, if you're getting stuck on certain memory training postcodes, retry button can help you get through those as well. I guess that's kind of what the Memo K2 switch is supposed to help with, but I feel like doing it manually might work better. So yeah, that's the retry switch right there. Below that, we have safe boot. And safe boot basically allows you to get into the system with, like, it won't, like, if you screw up your BIOS settings and you can't get the system to post, you hit the safe boot button, and it'll get you into your BIOS without wiping your BIOS settings. So that's pretty handy right there. Nice feature to have. Moving along the bottom edge, this side of the board, we can see we only have 4 SATA ports, which, you know, if you were actually planning to daily this board, that kind of sucks. But for extreme overclocking, there shouldn't be more than one device plugged in anyway, so who cares? Like, well, I don't really care. Moving along the bottom edge, we finally get to voltage read points, which are in the stupidest possible location ever. Like, see, I rip on ASRock for, like, putting the postcode here, right? I rip on... Gigabyte does it too. I rip on basically every motherboard vendor that decides that, hey, we're going to put buttons and postcodes and stuff on the bottom edge of the motherboard, and that's on full ATX motherboards, where the GPU generally is going to be somewhere around the middle of the board, you know, not on the bottom edge. But this is a reduced size MATX board. As in ASUS lopped off the, like, normally MATX boards would have 4, you could accommodate 4 PCIe slots, and ASUS lopped off the ability to do that with this board. And then they put the voltage read points right there. Like, the GPU is going to be right there. You're going to try to measure the voltages, and you're going to get your probes or your fingers into the fans of the heatsink of your GPU. Or, even better, if you have a GPU on LN2, the LN2 pot's going to be covering that up. Like, this is stupid. Why would you put it here? And if you're going to put it here, put it on a connector. But better yet, you know, you should have moved it to, like, this end of the board and put it on a connector, right? Like, I have no idea why they're still... Like, this board is 310 pounds. Like, that's $400 after tax. And it's just like, why isn't this on a bloody connector? Like, if they had it on a connector, then, you know, you can just plug in some kind of extensions. Like, then they could have a little extension that plugs into it, right? And at that point, it doesn't matter where this is, because you can just use the freaking connector, like, connected thing to measure the voltages instead. Like, I really like EVGA's approach to dealing with this, right? EVGA has the probe-it connector, it plugs in, and then it has a whole bunch of, like, probe wires attached to it. Those hook up to a digital multimeter, great. That's a good way to solve this. If EVGA did something like this with the probe-it connector, where it's in, like, the wrong spot on the motherboard, it's not a big deal, because you have some play with the, you know, connector. But here, it's just like, oh yeah, there's holes in the PCB, good luck stabbing them with the GPU installed. Like, really? Like, that is such a basic thing to not do that I really don't get how they decided. Like, also they have, like, unused spots. Just, why here? There's so many better places to put that. Anyway, so I'm not a fan of that design decision at all. But ultimately, it's not like, worst case scenario, you can just solder your own extensions onto that, I guess. But it's just like, then you're never going to get the board past RMA at that point. So, you know, rather annoying as far as I'm concerned that they've designed it like that. Anyway, up here we have, of course, the clear CMOS and the BIOS flashback button. So, usual ASUS ROG extreme overclocking motherboard loadout worth of features. Oh, well, it's also worth noting that it does have a clock gen right there. And as with all of the other ASUS boards, they do have some upgraded voltage monitoring well, not all ASUS boards, but all of the Maximus 11 boards, and also what they did on the Crosshair 7 Hero. They have upgraded voltage monitoring circuitry so that software voltage readings on this motherboard are much more accurate, because generally speaking, the voltage readings in software aren't really meant to be all that. Like, they're not designed to be as accurate as possible. And generally, the ASUS boards, I think Elmore said something like these will tend to measure, like, their circuitry will tend to measure something like 5 millivolts lower than it should be, like, than what the real voltage is. But it's really, like, it is way more accurate than the alternative of just using the usual circuitry for voltage monitoring. So that's a neat feature that they've added. Now then, VRM time. We have this lovely L-shaped block typical of mainstream Intel platforms. split right there, vGPU, and actually it's not just Intel platforms, it's really anything that doesn't have memory slots on either side of the chip, either side of the CPU socket. And then we, of course, have the vCore VRM. And this looks a hell of a lot like it's a 10-phase, doesn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 inductors, right? And no doublers. So, and this chip, unfortunately, is not one of the new... Like, there's a whole bunch of new voltage regulators from Infineon... Well, voltage controllers from Infineon, from Monolithic Power Systems. I think there's probably going to be some other ones coming out, but those are the two I'm aware of that have 10-phase... Like, they have 10-phase voltage controllers out. So, even if you didn't want to use doublers, you could have had a 10-phase here. But anyway, that is an ASP1405. And the 1405 is an 8-phase chip. And here it is running in 5 plus 2-phase mode. So this lovely 10-phase looking thing is, in fact, a 5-phase. I don't really have a problem with that, funnily enough. Like, the thing about phase counts is that they're not directly, like, having a high phase count does not necessarily mean your VRM is good. It's just that, generally speaking, if there's, like, if you do design a good 8-phase, right, well, it's easier to design a good 8-phase to move, say, 300 amps of current than it is to design a single phase to do 300 amps of current. In fact, if you did go with the single phase option, you're going to have a hell of a time making that work. And not be horrifically noisy and just terrible, inefficient, like awful in every way possible, right? So that's kind of why we have high phase count designs. The thing is, so I don't inherently have a problem with ASUS deciding to go with a 5-phase, right? I don't see a problem with that. It's just that this motherboard is rather expensive, and they have, they could have done other things. They could have certainly used doublers, which has some advantages and some disadvantages. So potential advantages is you might reduce your input ripple. The thing is, you can just redesign your input VR, like your input filtering, to compensate for that. So, you know, that's not a huge problem. It reduces your output ripple, but you can compensate for that with like, you can just change what kind of output filter you have, and then you can also crank up the switching frequency to compensate, which will harm your efficiency compared to a double design with lower switching frequency. But, you know, if your efficiency is high enough in the first place, who cares, right? Like, oh, the efficiency is worse by, you know, 10, like we're producing 10% or 15% more heat while achieving the same, you know, output quality, and not like, and the VRM is still not overheating. It's just like, well, who cares? And you save some money on getting rid of the doublers. So I don't inherently have a problem with this being a 5-phase. It's just not a 10, because there's 5 PWM signal, like there's 5 phases of PWM signal going into this VRM, right? Doublers phase shift the signals going through them. That's how you get more phases with doublers. So that's that. Like, the problem here is that ASUS advertises it as a 10-phase. It's a 5. There's nothing inherently wrong with it being a 5. It's just not a 10. Okay, so let's take a look at more detail at the actual power delivery componentry used, which is the ASUS favorite IR3555. And I've put that in the wrong damn place. I'm going to run out of space when we get to some other regulators. That is an IR3555 60 amp power IR stage, and that is well, should have it if I'm gonna go with it, right? POW IR stage, and that just means it's an international rectifier power IR power stage, and that is actually the product name of these things. Like, that is real. So anyway, these are kind of special. Well, they're 60 amps output capable, so, you know, really high power output. ASUS has been using these for ages, and they What else is there? They have over temperature protection, current monitoring built in, body braking mode, diode emulation mode, which diode emulation is pretty much standard for all power stages these days. Body braking mode you can get on basically all of the more advanced ones. But body braking mode is basically a transient response improvement thing where the power stage will basically, if you're coming out of load, the power stage will essentially stop running both MOSFETs. So there's a high side MOSFET and a low side MOSFET. And if you turn both of them off at the same time, you're going to force all of the power in the inductor that, like, the inductor wants to keep pushing current, but now there's basically going to be like a bunch of extra voltage drop through the body diode of the low side MOSFET of the power stage, and that's going to make it really easy for you to burn off your excess voltage. Because normally on load release, when say the output of the VRM goes from like 200 amps output to 45 amps output, the inductor is going to want to keep pushing a whole bunch of current, and it has nowhere to push that current, so you're going to get a voltage spike. Well, if you turn off the low side MOSFET, it's going to burn off the excess power in the inductor and reduce that voltage spike that you get on on coming out of load. So yeah, that's a pretty neat feature that all of the power IR stages have. Like 3553s also have that, 3575s have that. I think Intersil has their own equivalent technology. They call it something different. So yeah, but that is a cool feature that these things have. And the end result of ASUS using these, and actually like ASUS, what they're saying, their main justification for not using doublers is that it improves their VRM's transient response. So yeah, this is just like more transient response upgrades. But anyway, let's talk VRM efficiency. How efficient is this going to be pushing current into a 9900K? Well, at 400 kilohertz switching frequency, 1.3 volts output, and 5 volts drive, and I've actually talked to Elmore about this and ASUS, and actually everybody apparently with the power IR stages from International Rectifier, everybody runs them on 5 volts because there's there's apparently reliability issues if you run them on higher voltages, which is really odd considering that the entire data sheet is spec'd at 7 volts drive, Infineon at this point actually also says that basically these chips get less efficient if you run them on less than 7 volts. It's not a huge efficiency loss. It's something like 16% more heat output for any given current output. But yeah, there's a pretty major efficiency cost included by running them on lower voltage. But this is also much more convenient than having a dedicated voltage regulator just to get 7 volts. Because 5 volts you can just grab that off of the 24 pin. Now then, efficiency figures. 150 amps output. You're going to be looking at about 17.5 watts of heat, which is good. That's really nice and solid as far as I'm concerned. That's a good efficiency right there. And spread across, this many power stages. Admittedly, without any, there's no smart load balancing between the power stages. But what is worth noting is that MOSFETs, as they heat up, they get higher and higher RDS on. So inherently, basically they will sort of power balance themselves just based on whichever one is hottest. Whichever MOSFET, if one has a lower RDS on, it's going to pull it's going to have more current going through it. It's going to eventually heat up to the point that it has worse RDS on than the one than the other one, and then the other one's going to start, so they're going to kind of self-balance, but it's not, it's not necessarily ideal power balancing like you could have if you actually had doublers. Anyway, and that has a small, minor negative impact on efficiency because your 150 amps won't be ideally spread across all of the power stages. It'll be instead of having 15 amps through this one and 15 amps through this one, you might have 20 through this. Well, actually what you'd probably have is you'd have something like 13 through this one and then 17 through this one. Right? Because this one is closer to the rest of the other power stages, so this one's warmer, and so it's going to have more resistance to current through it, whereas this one's on the outer edge, and so this one's going to be running a tad cooler, and so it's going to be pushing more current. At least until it warms up, and then this one starts, catching up on the current output unless the temperature imbalance stays that way for forever. But ultimately, very, very minor, down, like it's going to very minorly change the total efficiency figures, so it's not really worth worrying about. 200 amps output. You're going to be looking at about 21.5 watts of heat, which I totally trust this heatsink to be capable of handling. Should not be an issue whatsoever. And going up to 2, and at this point, like, this is the reasonable range for normal users for this VRM. So, more than, like, 200 amps is already going to be hell to cool, because for 200 amps output, you're going to be looking at, like, 1.4 volts on a 9900K, and 9900Ks tend to be completely uncoolable once you exceed something like 250 watts of power, CPU core power consumption. This is around 280, right? Because 1.4 volts times 200 amps. So this is probably going to be uncoolable unless you have, like, delidded CPU, liquid metal lap die, that kind of situation going on. So not really this is not a realistic scenario. At this point, well, this is achievable potentially, but at outer limits, and, the efficiency is still great right there. So 250 amps output. At this point, we're just off to subambient cooling land and stuff that most people will never actually run into. At this point, you're going to be looking at about 28 watts of heat output, which is still, not that much. 300 amps. At this point, we're getting into what I would consider the purely theoretical current capabilities of this VRM. Because on paper, right, there's 10 power stages in here, and they can each do 60 amps. So theoretically, it would go all the way up to 600. But anyway, 300 amps output, you'd be looking at about 36 watts of heat, which still, that's a good efficiency right there. 350 amps output, you're going to be looking at about 45 watts of heat, and 400 amps output, and I'm doing that thing again where I'm going to run out of space. So 350, 45, and 400 amps output, you're going to be looking at about 58. So this is not the most efficient VRM we've looked at, but it is definitely plenty efficient for what it needs to do. Also, because it is, it is effectively 10 phases worth of components. It's just not running in 10-phase mode. It does also have a lot of surface area to spread all of that heat across. So it really shouldn't have any cooling issues in the sort of normal 9900K loading range. And then even like 250 amps, I really wouldn't be surprised. Like, I would still expect this to run plenty cool at 250 amps output. Like, you really shouldn't have any kind of problems with that. So yeah, I rather, like, this is a really solid 5-phase VRM, right? It's just not a 10. Like, it's a solid 5-phase. I don't really see a problem with it. I'm sure, like, there's a reason that, like, this motherboard already has a whole bunch of world records. So we already know that this VRM does fine in overclocking, like in extreme overclocking. So admittedly, that's not really a VRM thermal test, because motherboard, like, when you have minus 190 on the CPU, the funny thing is everything around the CPU very quickly turns into, ends up frosted over too. Like, like, it's pretty normal that if you're running anything full pot, your memory sticks are going to end up covered in ice. Your VRM is going to end up covered in ice. If you keep running for long enough, eventually even your power connectors are going to end up covered in ice. If you also have, like, GPUs on LN2 at the same time, at that point, if you run it for enough hours without ever warming back up to, like, higher temperatures, what tends to happen is on MATX motherboards and ITX motherboards as well, is eventually the entire board just ends up as one big block of ice. So it just completely freezes over. So in extreme overclocking scenarios, funnily enough, the VRM efficiency is not that much of a concern. It's mostly about VRM output regulation. And, it is only a 5-phase, but these things can easily go up to a megahertz switching frequency. And it's not going to have, like, you're not going to have cooling issues with the VRM on LN, with the CPU on LN2. So if if you wanted to, you could just max out the switching frequency of that ASP1405 to whatever ASUS restricts it to in the BIOS. So I don't really see a problem with this VRM for the intended application. In fact, even if you're on ambient cooling, and you want to, you might benefit from bumping up the switching frequency a bit. But generally, if you're not pushing huge amounts of current, you don't need to worry about you shouldn't need to change the switching frequency anyway. So yeah, I rather like the VRM. It's just a 5-phase. It's a really solid 5-phase. So then, moving on to the other, well, iGPU is of course 2 phases, that's why I said +2, but nobody cares about the iGPU, or at least I don't care about the iGPU. Down here we have a whole bunch of linear regulators from Anpec Electronics. This one's also part of that, and these are all APL 5337s. They're capable of up to 2 amps output. They drop their linear regulators. They basically convert. I think they're probably running off of 3.3 volts here, and they're converting 3.3 volts into your PLL termination voltage. What else? CPU PLL voltage, DMI voltage. There's like a whole bunch of all of those special voltages that the RSVD switch has to change. Yeah, they're taking care of these regulators right here. This is completely adequate. You don't need anything more substantial for those. They're very low current rails. Honestly, generally, funny story with these, actually, these voltages, if you aren't building an extreme overclocking motherboard, things like, say, PLL termination, will generally, which is the actual voltage, because ASUS likes to relabel the voltages for some reason, to keep it secret what voltages they're they consider it their LN2 overclocking secret sauce, but that voltage in the Intel datasheet is actually called VCCPLLOC, and on normal motherboards where you wouldn't worry about extreme overclocking, VCCPLLOC is just tied to the voltage of the memory regulator. So normally memory is at 1.2 volts, so that's what normally VCCPLLOC would be. So this regulator doesn't really have to exist at all unless you're doing extreme overclocking. So yeah, and that's one of the cool things. It's kind of interesting, how Intel basically this is a voltage that wouldn't necessarily need its own pins in the socket, and Intel went ahead and just added them because it's you need it for extreme overclocking. So here's a dedicated pin for just that. A couple. I'm actually not sure how many pins it's on, but yeah. So that's pretty cool that, Intel accommodates extreme overclocking like that, because really those voltages have no other use. All of them are designed to be otherwise, on normal platforms, they would just run off of other regulators anyway, typically off of VDDR or something. So yeah, but anyway, so that's the voltage regulators right there. Then here we have VCCSA, and that's controlled by this chip right over here. That's a single phase, and let's just put VCC. So that powers the system agent, which that's like your PCIe interface and part of your memory controller as well. Voltage is mostly required for memory. This voltage, you mostly need to adjust it when doing memory overclocking. And that is generated with two... so you have, one high side... nope, that's the low one. That's low, high side. And those two MOSFETs are 4C10Bs, which are completely comparable to the 4C10N. ASUS just uses the B variant. I'm not sure what, I asked Elmore about this, and he was just just use the N data sheet. It's the same thing. So that's that. The voltage controller for that is an APW8723, and that runs at a fixed 300 kilohertz. And this is a minor rail. You really don't have to worry about it. This is fine. And for VCCIO, we have this regulator right here, which is a fully integrated buck converter from Texas Instruments. And that is which is that chip right there. And that is a TPS 53, I want to say. No, 51362. And that's capable of up to 10 amps output, which is it's not completely overkill for VCCIO. It's adequately sized for VCCIO, because generally speaking, VCCIO is never going to exit the single digit current range, and not necessarily even cross the sort of 5 amps output range either. So that's completely adequate as a single phase power supply for that. And I think this set of VCCSA and VCCIO VRMs is standard for all of the ROG boards, just because I don't think they want to redesign these. So those are going to be the same everywhere. And for memory power, we have the ASUS standard of the ASP1103 and some generic, like, I'm not actually sure what they are, but in the past, they're not very high spec. We have a 2-phase memory VRM right here. And so phase 1, phase 2. And yeah, you have some nice little reduced package size MOSFETs for that. Because memory doesn't pull enough power to really be worth worrying about. So that's how ASUS typically powers it, and there's no real problem with that. What's kind of interesting with this board that I've noticed is that, well, for one thing, they've really redesigned the output filter of the memory VRM, which is partly because the M.2s go into this area, so you can't have your typical cylindrical, Nichicon FP10K capacitors everywhere, which would normally be used for VDDR. But they've also, like, instead of just going for like a couple 470 microfarad SMD capacitors, they've gone for a whole bunch of these 150 microfarad capacitors, and they actually have them also on the back, right? Like, that is pretty extensive as far as I'm concerned. That seems like they're actually trying to upgrade the output filtering for the memory power instead of just like reduce the physical height of it. Because if they wanted that total bulk capacitance, they could have gotten that in like half as many capacitors, no problem, or even as like 1/3 as many capacitors without really, having to go this far. And also they just have like this strip of multi-layer ceramics, which is just, that is definitely just like they wanted to upgrade the output filtering. So that's kind of interesting that this probably has better memory power delivery than a lot of the past ROG boards. I'm not sure if that'll actually impact memory overclocking. It could be interesting to test that. And of course, it's like I'm just going to... I don't have that many memory kits, so I'm just going to run the stuff I usually run, and we'll immediately notice if there's any differences in overclocking range. And if there is, then it's probably down to the new output filtering, because that controller and this set of MOSFETs and chokes has been standard for ASUS memory power for a while now. So, this is the only major difference. Well, they could have also changed the trace layout for this board. Of course, being an extreme overclocking motherboard, you only get 2 memory slots because that's optimal for your memory trace length and memory trace layout, because there's just less of the traces. And also, the way the memory traces are wired for 4-DIMM motherboards, a lot of the traces actually like go to 2 memory slots. Like they're shared between the memory slots. So there's a whole bunch of extra parasitics on the memory traces. If you have 2 memory slots per channel, there's a whole bunch of extra parasitics on the memory traces, which reduces the signal integrity, which is why basically 2-DIMM boards dominate in memory frequency overclocking in general. So that's worth noting. And really, memory frequency is not the only thing they're great at. Just even like very tight timings as well, that just better for memory overclocking in general. So that's, I think that covers everything at this point. I mean, you have PCH power down here. I assume this is a small integrated buck converter for VPP. I think that's PCH. I've not actually bothered to check. It's not that important. Yeah, I mean, this is what you'd expect from an ASUS extreme overclocking motherboard. It's just that it is very, very expensive. Unfortunately, like, the thing is, it's hard to compare because ASUS doesn't really have doesn't currently have a competitor in this niche, right? Like, what other extreme overclocking motherboards exist on Z390? Oh, the Z390 Dark from EVGA, which we currently don't know how much it costs. And it currently, like that's pretty much all I can say. Like, it exists. I know some stuff about it. Can't share. I'm excited for that board. But, yeah. And that board is full ATX. So, and I'm not, like, without knowing the cost of that, it's really hard to say if this is overpriced. I mean, I really like everything on this motherboard. But it's hard to say if, ASUS is not... like if ASUS is overcharging or not. I personally think like this is more expensive than I think the past Apex motherboards, and I don't really think there's that much of a difference to justify that. I mean, yes, this is a better VRM than they've ever had on a, like, the Maximus 9 Apex or the Maximus 10 Apex. This is a better VRM. No doubt about it. But this is basically the same memory VRM. And they've always had this. That hasn't changed. They've always had this. That hasn't changed. They lopped off half the they lopped off the bottom end of the PCB. You know, they have less PCIe slots than ever before. So yeah, I feel like this might be, you know, this might be a bit expensive, even comparing against ASUS's old extreme overclocking boards. But then again, they are kind of cramming it with, you know, features for well, I don't know that it has gaming features, but it, like, they did go out of their way to make sure that, you know, you have the double capacity memory sticks, so that if you want more than 32 gigs of RAM on this platform, you could still get it by buying memory sticks that are essentially like, what are they going to be? They're going to be like 32 ICs, I think, each, to get 64 gigs. I can't remember, but basically, like, they're non-standard memory sticks, because the highest density you can currently get, like, normal memory sticks, are like 16 gigs a stick for mainstream platforms. Obviously, there's server sticks, but those don't work on mainstream platforms. So yeah, ASUS did go out and, like, collaborate with some memory vendors to create those memory sticks, but I don't know, that doesn't seem like that useful a feature to pay, you know. Well, this is like 60 pounds more than the Maximus 9 Apex. Admittedly, that one was like, the 10 was more expensive as well, but yeah, it's like, it's a nice board. It's also really expensive. Or, well, really expensive. It is rather expensive. So yeah, I'm super thankful to the guy who actually paid for the board, because honestly, once it went up in retail and I'm like, oh, it's 310 quid. You know what? I'll just send for EVGA to send me the Dark instead. I'm sure I'm gonna be fine without an ASUS board this time around. So yeah, that is it for the Maximus 11 Gene. It's a 5-phase, not a 10. It looks, you know, it's already proven to be great at extreme overclocking. No, and I mean, there's no surprises there. The VRM is better than what ASUS has run ever in, like, really ever in the past. Yes, it has less phases. You can, you know, work around that. So overall, the VRM is still better than what they had in the past. And yeah, that is it. At this point, this video is really long, but this is like a complicated motherboard, so that's my defense. Thank you for watching. Like, share, subscribe. Leave any comments, questions, suggestions down in the comment section below. And if you'd like to support actually hardcore overclocking so that I can buy other interesting motherboards that are rather too expensive from brands that I've insulted for certain design decisions. Funnily enough, I insulted Gigabyte quite a lot, I think, on other platforms, and they've, you know, taken it in stride recently. And here, like, well, I don't even want to message ASUS, but anyway. Yeah, if you'd like to support what I do here with actually hardcore overclocking, I do have a Patreon. There's also t-shirts you can buy. You can find a link to all of that down in the description below. And yeah, that is it for the video. So I'm going to hit that stop button before I make it any longer.